Good afternoon, and thank you for joining us for the 2021 Arden L. Bement Jr. Distinguished Lecture. As Purdue University's Executive Vice President for Research and Partnerships, I am honored to welcome you to this event, an important opportunity to learn about the exceptional work of one of your colleagues. The Arden L. Bement Jr. Award is Purdue's most prestigious research award in the pure and applied sciences and engineering. I am pleased to have in the studio with me this year's awardee, Michael Manfra, the Bill and D. O'Brien Distinguished Professor of Physics and Astronomy in the College of Science, and Professor of Materials Engineering and of Electrical and Computer Engineering in the College of Engineering. Professor Manfra also serves as the Scientific Director of Microsoft Quantum Lab, West Lafayette, and is an important contributor to the Quantum Science Center, the Department of Energy Quantum Information Science Research Center that was funded in 2020. I also have with me John Finley, Professor and Department Head of Physics and Astronomy in the College of Science. Professor Finley nominated Professor Manfra for this award and will provide his introduction. He will also moderate the Q&A following the lecture. During the event, we will accept questions through the Q&A module and address as many as possible immediately following the lecture. In addition to live streaming of the event, a recording will be posted on the EVPRP website. Before I turn things over to Professor Finley, I would like to offer a brief background on the award. Purdue Distinguished Professor Emeritus Arden Bement and his wife, Louise Bement, established this award to honor outstanding accomplishments by a Purdue faculty member in pure and applied science and engineering. The award, endowed by the Bements in 2015, recognizes the consistently impactful innovations and discoveries by Purdue's faculty. Bement Award winners are nominated by their peers, selected by a committee of distinguished faculty, and are approved by the Executive Vice President for Research and Partnerships and the President of the University. I will now turn things over to Professor Finley.
It is my distinct pleasure to introduce Purdue University's 2021 Arden L. Bement Jr. Award winner, Professor Mike Manfra, the Bill and D. O'Brien Distinguished Professor of Physics and Astronomy, Professor of Materials Science Engineering, and Professor of Electrical and Computer Engineering in the College of Science. Mike received his Bachelor of Arts from Harvard, followed by his Master's and PhD from Boston University in 1999. Mike spent 2 years as a postdoctoral member of the technical staff, Bell Laboratories, Lucent Technologies, and in 2001 became a member of the technical staff of Bell Laboratories, where he carried out research in low-dimensional electron systems. In 2009, we were fortunate to hire Mike as the William F. and Patty J. Miller Associate Professor of Physics and Astronomy, Materials Engineering, and Electrical and Computer Engineering. Mike was a Keck Foundation awardee in 2013 and was promoted to full professor in the same year. He was named the University Faculty Scholar in 2013. He was elected a Fellow of the American Physical Society in 2015. And in 2016 became the director of Microsoft Quantum Lab, Purdue, one of a small handful of Microsoft quantum laboratories around the globe. In 2020, Mike became a distinguished professor of physics and astronomy. Since 2018, he is a member of the Burke Faculty Leadership Council, and Mike has served as an industrial consultant on quantum computing, as well as an advisor on government programs. Mike's research focuses on growth, device fabrication, and electron transport properties of low-dimensional semiconductor systems and hybrid superconductor semiconductor systems. Development of novel qubit modalities is now a primary focus. Work includes use of Fabry-Perot interferometers to study anyons in fractional quantum Hall states in the two-dimensional electron gas in aluminum gallium arsenide heterostructures, and engineered superconductivity in super-semi heterostructures. This work complements ongoing efforts with spin qubits in lithographically defined quantum dots. Direct observation of anionic braiding statistics is a significant research highlight for his team. Mike is widely recognized for his contributions in semiconductor physics and their fascinating quantum behaviors. His external evaluators have uniformly recognized Mike's skills with comments like, "Mike belongs in the select group of a handful of physicists who not only excel in growing the highest quality semiconductor devices, but at the same time have made spectacular physics discoveries." And while Mike is already of tremendous stature in the field with an unusual level of depth and breadth, what he has achieved now is a major milestone of the field. This recognition of his recent work on anion statistics is best summarized by this statement: "He has done much fine and well-respected work. However, his recent work involving the direct interferometric detection of fractional braiding statistics in a fractional quantum Hall fluid is an entirely new category. It is a major accomplishment, one for the textbooks." I am confident that Mike's dozen graduate students, 10 postdoctoral associates under his supervision, and numerous undergraduates that have worked in his labs would attest to Mike's depth of knowledge and creativity. Please join me in welcoming the 2021 Bement Award winner, Distinguished Professor Mike Manfra.
Okay, well, I first want to thank both Teresa and John for those really flattering introductions. And I want to thank John not only for the putting my nomination forward and championing it, but also John has been our department head over the last 6 years, leading the Department of Physics and Astronomy. And as we all know, it's been a difficult couple of years, and John's stewardship of the department has been exemplary. So I want to thank him for that. I also want to thank now Erica Carlston, one of my faculty colleagues in physics and astronomy, who helped out with the nomination, and John and Erica's support was really helpful for me being able to give you this lecture today. Okay, and so as I get going through the lecture, I am going to pause, if you'll indulge me, to acknowledge people who have made significant contributions along the way. We're going to talk about something rather narrow set of experiments today, but obviously to get to that point took a lot of effort, and a lot of people influenced that and made it possible. So I guess first I want to thank my wife Juana and daughter Katie. And the last few years have been very hectic with lots of travel and responsibilities in various domains. And they've been very supportive and understanding of that, but also keep me grounded and let me know what's important. So here's just a picture of them from this summer that we went to Zion National Park, and they told me, "We're going to Zion. You're coming, right?" And so my daughter certainly lets me know what's important and what's not. So I want to thank them for their love and support. Okay, so why are we here, or what am I going to talk about? And I'm going to talk to you about an object called an anion, which is rather unusual. But first, to give you some grounding in what we're talking about, I should consider what we do as physicists and what our current understanding of the laws of nature are. So as physicists, we'd like to break things down into the elementary elements. What are the particles that make up matter, and what are the rules that govern those fundamental particles? And broadly speaking, there are two classes of elementary particles that we know of: fermions and bosons. And these are distinguished by their statistical properties, how they behave in aggregate when they're interacting or in the presence of other bosons or fermions. And examples of fermions are electrons, quarks, muons, protons. And examples of bosons are photons, gluons, gravitons. And this distinction really comes down to how these particles behave when you interchange their positions. Fermions, if you exchange two particles or permute the location of two particles, the wave function is anti-symmetric. It picks up a factor of -1. And bosons, on the other hand, if you exchange two particles, they're symmetric under that permutation, and the wave function stays the same. Now, this has very important consequences for how they behave. For example, fermions obey the Pauli exclusion principle. They don't like to be or cannot be in the same quantum state. They're antisocial. And so that property alone can be used to characterize the properties of normal materials. The conduction properties of metals, semiconductors, and insulators can be arrived at by simple symmetry arguments and the Pauli exclusion principle, that no two fermions can exist in the same quantum state. Bosons, on the other hand, are very social. They like to flock together. They're happy to be in the same quantum state under the right conditions. And dramatic result of that type of behavior is Bose-Einstein condensation and superfluidity. So these defining statistical properties actually have very demonstrable impact for the properties of these types of particles in the aggregate. Now, that's in 3+1 dimensions, the normal world around us. That's all there is. There's fermions and bosons, at least that's what I'm aware of. But in the early 1980s, theorists started to conjecture that in reduced dimensions, there may be a different type of statistics available. And especially in 2 dimensions, there may be something called an anion. Anion is just a play on words that can have any statistics. Frank Wilczek coined the term. But that results in these lower dimensional systems the possibility for very dramatic behavior. Anion braiding statistics are unlike bosonic or fermionic statistics. If we exchange 2 particles or wrap one particle around another, the wave function doesn't change by a factor of -1 or 1. It picks up a phase that's particular to that particular state. It can have fractional statistics. Also, the units of charge for anions can be a fraction of the electron charge. It's a very unusual idea that you can have lots of electrons in aggregate, but the fundamental objects in this system behave as if they have a fraction of 1 electron charge. And while this was a theoretical conjecture starting in the 80s, there was then speculation that it may be actually realized in a quantum Hall system. And I'll tell you what a quantum Hall system is in a moment. That's what we study, among other things, in my laboratory. And so the key result that I'm going to try to tell you about is that in the fractional quantum Hall state at filling factor 1/3, I'll explain that in a moment, the quasiparticles do carry a fraction of a charge, and they obey anionic braiding statistics with a statistical angle of 2π/3. And that's the subject matter of this talk. Okay. So of course I have to tell you what a fractional quantum Hall effect is, or a quantum Hall effect in general. And actually it's not too hard. The experiment, the rudimentary experiment, is rather simple. If I have a semiconductor structure that hosts a 2-dimensional electron gas, that means it can only move in the XY plane but not in the vertical direction. So it's actually as if a billiard ball is confined to the surface of the table but can't bounce around up and down. I can take a slab of this semiconductor and do a very simple measurement. As I show you on the left-hand side there's basically a rectangle of this 2-dimensional electron gas. I hook up some contacts to it and force a current to flow from one end to the other. That's XX that I'm showing in this particular cartoon. And I do very simple things. I monitor the resistance along the length of the sample, and I monitor the resistance across the sample as a function of magnetic field. The magnetic field is perpendicular to that 2-dimensional plane. And so all I'm doing is measuring a resistance or 2 resistances. And classically, this should be very boring. The longitudinal resistance should be flat, not have any magnetic field dependence. And the Hall resistance, that transverse resistance that's measured perpendicular to the direction of current flow, should be a straight line that is proportional to the applied magnetic field and inversely proportional to the density of electrons that exist in my 2-dimensional electron gas. Now, if I look on at the data on the right-hand panel, This is in a modern gallium arsenide sample that we measure in our laboratory, and this is measured at very low temperatures, nearly absolute zero. And in an applied magnetic field, you see something quite different. The blue trace is the longitudinal resistance, and rather being a flat line with no magnetic field dependence, you see this spiky behavior where the resistance suddenly shoots up but then drops back down to zero in certain what we call magical places in magnetic field. Concomitantly, the Hall resistance does have a linear component, as you see, but at certain intervals in magnetic field, it loses the dependence on magnetic field and becomes completely flat. And in these regions, the Hall resistance is quantized to extraordinarily high precision to multiples of h over e squared, two fundamental constants of nature. So this actually, you'll see some numbers that I've listed out. Nu equals 1, where you see in the center of the plot between 4 and 5 Tesla. You see a very wide plateau, very, very flat and sharp, and at the same time, the longitudinal resistance dropping to zero. Current flows without dissipation. And this number, this filling factor, nu, is actually important. If you just look at the single particle bands in a magnetic field, you'll see that the electron levels develop into a series of levels called Landau levels, and they are highly degenerate, meaning the band is flat, all the electrons can sit at the same energy. And there is a gap between that level and the next available level given by h bar omega c, which is just proportional to magnetic field. So if it so happens that the Fermi level in the system is in the gap between two Landau levels, you will see these extraordinary transport response, the flatness of the Hall resistance and the zero in longitudinal resistance. This means I have one Landau level, say at nu equals 1, completely filled. The Fermi level is in a gap to the next available state, and that's the circumstances under which we see something called the integer quantum Hall effect. Now, it turns out that Hall plateau actually has some significance, a topological significance. And it's an invariant of the system. It doesn't really depend on the details. As long as you meet these conditions, no matter some microscopic details, you'll see the same behavior, independent of material system, independent of disorder, all sorts of things. And that number you see there is really a quantum number. And nu equals 1, that state can be associated with the quantization of electrical charge. Okay, so nu equals 1 of electrons. This is normal electrons we're talking about. But you'll also see in the pattern that I'm showing in the plot all sorts of spikes and zeros in the longitudinal resistance and other locations where we have a flat plateau, but the filling factor, the ratio of density of electrons to the magnetic field, is at fractional filling. 2/3 is shown in the plot. 4/3 is shown in the plot. Now, those features cannot be explained by single particle physics because say at nu equals 2/3, all the electrons reside in the lowest energy, single particle energy level, and there's available states. There shouldn't be any anomalies in transport there without interactions. The point is very strong interactions in a high magnetic field create a gap we wouldn't have anticipated. But the fact that there's precise quantization also implies that there's a conserved quantity, which is the fractional charge. Actually seeing that behavior at all implies that we have fractional particles. Okay? Now, these quasi-particles or excitations have been conjectured to have fractional charge from the earliest days of the fractional quantum Hall effect. Bob Laughlin in 1983 said the appearance of these states necessarily implies that the charge carriers are not electrons, but fractionally charged quasi-particles. For the nu equals 1/3 state, not shown on this plot, but the first one discovered, it implied that the effective charge was the bare electronic charge divided by 3. Okay, so that's 1983. Shortly thereafter, Bert Halperin and Wilczek and collaborators said that not only are they fractionally charged, but these quasiparticles should have anionic braiding statistics. There's a statistical phase that is neither fermionic nor bosonic. And in the case of this particular state, the statistical phase should be 2 pi times the ratio of the effective charge to the bare electron charge. So look at the dates. I call your attention, 1983 and 1984, and then I'll mention when the experimental confirmations took place. So what do I mean by braiding statistics? Just to be in a very simple cartoonish fashion. These two spirals or vortices represent quasiparticles. If I were to take one quasiparticle and wrap it around the quasiparticle at the center using the motion I've shown you here, you would think, well, what's the big deal? I just took one particle around the other and it's back at its original configuration, so that shouldn't have any effect. For anyons, that's not actually the case. The effective wave function for those two quasiparticles builds up a phase that is 2 pi times E star over E. And if we're working at the 1/3 fractional state, that implies anionic phase of 2 pi over 3. So this is very different than what we would have expected for our normal bosons and fermions. Now, because the theorists tell us so, it doesn't make it easy to see. And I'll point out that the determination of fractional charge, or the confirmation through quantum shot noise measurements, took place in the late 90s, many years after the initial discovery of the quantum Hall effect. And Rafi Di Picciotto, a former colleague of mine, working at the Weizmann Institute, was one of the first to actually verify this, along with a group in Saclay in the late 1990s. I'm giving you a talk in 2021 about anionic braiding statistics, so that must have taken a while too. And that's the story I'd like to tell you right now. So we're interested in phase, and you can imagine from optics and experience with optics, interference experiments are the way they have exquisite sensitivity to phase and phase differences. So what we use in our system, this two-dimensional electron gas in gallium arsenide, we build the electronic analog of a Fabry-Perot interferometer. Now, we have beam splitters and an interference chamber, and I'll show you that now. So just in cartoon, just looking at the cartoon, the blue region corresponds to the two-dimensional electron gas. These yellow lines and T's that you see, those are gates that are on the surface. They're used to locally deplete, remove the electrons in the 2D gas. They form the boundary of our interference chamber. Now, the two constrictions you see, one located near the source contact, one located near the drain contact, are the analog of our beam splitters. They partition the currents that flow in the system to generate the interference. So imagine my current comes in, current in the quantum Hall regime flows along the edges, it comes to this constriction, it's partially backscattered to the other edge, back to the source, but most of the current circulates around the interior of the interferometer until it reaches the second constriction, called a QPC, where some of it again is backscattered and circulates around the interior of the chamber and then rejoins the current that was scattered at the original QPC. Now, this is, as long as the transport is coherent, can be an interference process, and we can extract a lot of information from this. In fact, the theorists told us all the way back in '97 that we could measure the effective charge, the anionic phase, and properties of these edge states, Luttinger liquid type behavior, all from this simple geometry. So sounds simple, right? So the backscattered current should have a term that varies periodically, here cosine theta, where this theta now is not the anionic phase but the interference phase between the two interfering beams. So if we're just dealing with normal electrons, this interference phase will be nothing but the Aronoff-Bohm phase. The electron circulating around the interior circulates around a magnetic flux and generates a phase, and that's different from the phase generated at the original QPC, so that would amount to the phase difference. So here theta, which is the interference phase, is just 2 pi times the area, the interior of the interferometer, times the magnetic field piercing through the center of the interferometer, divided by the magnetic flux quantum. The magnetic flux quantum is just a ratio of two fundamental constants, H over E. So we can measure interference by measuring the electrical conductance across the device. We can operate the device by changing the area by these T gates, the yellow T gates. We can squeeze the area or expand it by changing the gate voltage, or we can change the flux that comes through the chamber by changing the magnetic field. And under these very simple operating principles, we would expect lines of negative slope of constant phase in the magnetic field gate voltage plane. So if you imagine, I want you to keep this sort of idealized picture of what the conductance looks like. This is a two-dimensional plot of conductance. The red lines are lines of constant phase. The blue lines are another phase. And it has sort of this barbershop pole type behavior. The intensity corresponds to the actual backscattered current. Okay, that's what we should expect. Let's see if we can actually do it. Then if we add, we go, and that's with normal electrons. If we go in the fractional regime, there are two very strong modifications. First, the interference phase becomes proportional to the effective charge, that extra term in the Aronoff-Bohm phase, and the interference term becomes directly dependent upon the anionic phase. The anionic phase of whatever state we're in times the number of localized quasiparticles within the system. So if you look at the figure, that little spiral corresponds to a localized quasiparticle, and if the circulating, interfering quasiparticles going around the chamber see that phase, it will change the interference. So how would this be modified? Well, if I change the quasiparticle number by 1 or -1, I can only add or subtract individual units of quasiparticles, I should see phase slips, jumps in the pattern. This nice periodic structure should be interrupted by phase slips when particles enter or leave the chamber. Okay, so what are the demonstration experiments? These are the ones I'm here to talk to you about, and there was two that occurred, took many years to get to this point, but over starting in 2018, 2019, 2020. And the first one was the demonstration that you could actually see this Aronoff-Bohm-like interference in the fractional quantum Hall effect of their edge modes. And this was a problem for reasons I can explain briefly, but it was difficult to achieve. And the innovation here was a new heterostructure and device design that I'll talk about in a few minutes, but this really was a device design innovation. And the second experiment that I'll tell you about is using that type of device to directly observe anionic braiding statistics. And that's in the second plot. Now, based on what I just, on the right hand, on my right hand side, you see the plot where you see this is actual data of those constant lines of phase, of conductance, and they have the proper negative slope, as you'd expect, but they are also interrupted by these glitches, which are actually reproducible and of a proper magnitude and are consistent with measuring an anionic phase. So these are the two experiments that I'll try to briefly run through, but I do want you to take note of the first author on both these. This is James Nakamura. And what I really want to emphasize is that James was my graduate student and now a postdoc, but he has been the experimental lead on these efforts. He's just truly an extraordinary researcher and has really been an intellectual force, and it's been very gratifying to work with him. He's now teaching me more than I teach him, and I want to make sure that he's properly acknowledged. I think he will be in the years to come, and he's off to a great career. Of course, he was aided by some of his colleagues in my group, Saeed Falahi, the top, Jeff Gardner on the lower left, and Shuang Liang, students that helped out with making the materials in the first place. So it was a team effort, but Jimmy was really the driving force here, more so than I was. Okay, so what was the first innovation that allowed us to move forward? Well, we actually came up with a modified heterostructure. And this is a aluminum gallium arsenide heterostructure grown by MBE, and it's shown on the far left. The region of interest is the 30 nanometer gallium arsenide quantum well that's sort of in the middle. But the innovation, and this was really work with of Jimmy and trying to get the right parameters in place, we put 2 quantum wells in close proximity, in situ. So they're only 25 nanometers away from the main central quantum well, and that has made all the difference. So if I look at the middle panel, I'm showing you now a band structure diagram. This is in the Z direction along the growth direction. But the important point is the electron gas, the blue trace corresponds to the electron density. The electron gas we're interested in is in the center well. It has a density of about 1 times 10 to the 11 per square centimeter. Now, that's the one we want to probe and do interference with. But in very close proximity, we've put 2 very high density electron gases. And we're using this basically to put our device of interest inside a parallel plate capacitor. And that has all sorts of benefits, including screening and allowing the device to operate in the regime of interest. Of course, that comes at the expense of device complexity. We now have 3 two-dimensional electron gases all in parallel, and if you try to measure transport, it'd be a big mess. But a unique device design allows us to probe that central 2-DEG with the benefits of the screening generated by the 2 proximal 2-DEGs and controlled transport through it. So what this actually ends up with is an interferometer with in situ screening layers. So on the left is a cartoon of the large scale device. At the very center sits this mesoscopic device that's only in the center. I can show you a SEM image here on the right. Makes it very small. We want to make the device very small, so it's highly coherent. The electronic transport is coherent. But we've added these screening layers so that we can control mesoscopic effects. So small device with high coherence, good, and we've controlled mesoscopic effects. And so if you zoom out and look at this is the real device that we originally measured anionic statistics in, it looks like this. This device sits at the bottom of the dilution refrigerator at about 10 millikelvin. Okay, in around 2019, we saw for the first time this pajama plot that it's called in the field of negatively striped lines of constant phase, like the theoretical prediction I showed you earlier. And this is at the 1/3 state, and you see that we have Aronoff-Bohm interference. And this was, at least for us, an accomplishment because we got it to operate at least in the right regime. Now, in this first experiment, we were able to measure the effective charge of the charge carriers, which was 1/3 E, but that's not really a surprise. That had been measured in the late 90s, so we weren't the first to do it. But it at least showed us that our device was working. Now, we weren't completely in the right regime in this first example to see the anionic phase slips, but with help of theorists, we redesigned the device, the heterostructure and the device, to account for some mesoscopic effects. And here's our original data set. Remember, I mentioned that this interference phase has a Aronoff-Bohm component to it. That's the first part in the equation. And then the anionic contribution, that if we change the number of anions in the sample, that we'll see phase slips. And these phase slips, they look like noise, but they're not. They're reproducible. They actually correspond exactly to what we expect in terms of the phase slip. And we've done fitting and analysis of this. And if you take the average of these phase slips, delta theta experimentally is minus 2 pi times 0.31, which is pretty darn close to theta anion, the theoretical prediction of 2 pi over 3. So we took this as confirmation, I think the first confirmation of anionic statistics in the fractional Coulomb Hall regime. So completing the picture of noise measurements that were done to see that the charge was 1/3. Now we see that the phase factor, the statistical phase, is 2 pi over 3. Okay, I'll try to move quickly here. The reaction of the research community was fairly swift, actually. There was a lot of, for me at least, unexpected response to it. And the amusing thing is this came out before the paper was actually published. We had just put it on the archive, and this response came out in July while we were waiting for the paper to be reviewed and eventually published in September. So you can say, oh, that's nice, but actually for me, it kind of made me quite nervous. This better be right, and we should be able to reproduce it and move forward from there. So I'm happy to say, at least so far, that that actually has been the case. There's a more complex theory of how these devices should operate, and I'm showing you data from a still more over a broader range of magnetic field, and that we're trying to work in a different regime. And so you still see the phase slips as predicted, but as you move outside the center of the fractional quantum Hall state, you see other periodicities, changing the pattern, lines of negative slope going to flat, and then this modulation, this periodic modulation. And in these outside regimes, the periodicity changes to phi naught, the fundamental periodicity h over e squared, h over e, sorry. And all of these in detail now, we can control the device, reproduce it, and actually study other aspects in transport that are directly related to the presence of anyons. This type of behavior wouldn't be true if they are fermions or anything else. So this is comforting, and it allows us a way to move forward to probe more deeply and compare with theory the behaviors we might expect of these anionic excitations. So, and if you zoom in really close, by design, these phase slips are much sharper. As you can see in the zoomed in, it's pretty clear that there's discrete phase jumps. They're reproducible. They come exactly at the values we expect. So all this is good so far. Of course, nothing is ever the final statement, but everything we've done so far is consistent with expectations. So if I were to summarize the findings to date, we have demonstrated in a novel device design direct observation of anionic braiding statistics. What really enabled this was a novel heterostructure design and device design that really facilitated the results. And I'm happy to say variation of device parameters demonstrates fine control and the exploration of new effects, and that's an ongoing effort. Now, if you indulge me, I know I'm running long, but I do want to acknowledge people and that helped this whole process to work and make a connection to my previous life to Purdue, and I think it's at least entertaining to me story. So I started my career at Bell Labs in Murray Hill, New Jersey. And for me, at the time as a young condensed matter experimentalist, this was Xanadu. It was a place to be. But I got lucky, and I got to work with a fantastic set of colleagues. Now, I know this picture doesn't look like the most illustrious group, but if you let me show you, this is the semiconductor physics group around 2000. The person actually taking the picture is our department head, Steve Simon, a theoretical physicist, now at Oxford in the UK, who did a lot of foundational work in the quantum Hall effect and interferometers in particular. If I look at the back row, on the far left is Bob Willett, the person who is responsible for the observation of the 5-halves fractional quantum Hall effect and composite fermions. These are features in the quantum Hall regime that are particularly important. Next to Bob is Lauren Pfeiffer, the world champion in MBE growth, and who took me into his lab and taught me how to develop techniques and advance MBE. Right in front of Lauren is Ken West, his able assistant, who is just a technical master. After that, that's me. And then to the right is Kirk Baldwin, who was a technical person at Bell Labs and working with Horst Stormer. Now, the person to the far left with the dark hair, younger guy, is Rafi Di Picciotto, the person I mentioned who had measured the 1/3 charge just a few years before. So this was a great opportunity for me to learn with a great, real masters of the field. And I want to continue because there's a connection to Purdue. So who was missing from this photo is Horst Stormer and Dan Sui. Now Horst, the year I arrived, Horst and Dan won the Nobel Prize. And Horst was still at Bell Labs, but also starting his time at Columbia. Now Dan Sui had long left Bell Labs. In the mid-'80s, I think he went to Princeton. But nevertheless, Dan was a frequent visitor to Bell Labs. In fact, he would come around basically every week and spend a lot of time with us. And I was never quite sure why. Princeton's actually not that close to Bell Labs, but he was a very regular visitor, and we have long talks. And the guys used to joke, well, he's trying to get away from his students, but actually I think he just enjoyed the camaraderie in talking about physics. Now, there's a connection here because Dan did a lot to populate the condensed matter group at Purdue. Specifically, Gabor Chatti and Lena Rokinson, I believe, were postdocs in the group in the early 2000s, and Yang Chen was a student. Now, in particular, I met Gabor through Dan, and either he came to Bell Labs one time, or I don't recall, or I went down to Princeton, and Gabor was working in his lab. Now, Gabor left his postdoc to come to Purdue. And since that time, Gabor is a world-leading expert in ultra-low temperature physics and has made major contributions to the quantum Hall effect himself. But a few years later, that was around 2000, 2008, I bumped into Gabor at an APS March meeting, and he said they might be looking for people at Purdue. And I said, oh, that's interesting. I talked to Dan about it. He said, yeah, it looks like a good idea. So these people were actually crucial in recruiting me to Purdue in the first place. And it was our connections through New Jersey and Dan Sui that led to that, my arrival in Purdue. And Gabor and I have collaborated on many projects. He's, as I said, an extraordinary scientist himself, and he's been very helpful along the way. Now, when I came to visit Purdue, there was the Burke Nanotechnology Center that had just recently been established. And for me, this looked like a great opportunity in terms of the facilities to actually make happen what I wanted to, sort of recreate Bell, if I could, on a smaller scale. And if this hadn't been here, it's unlikely I would have been successful. And in the early goings, Tim Sands, who was the director at the time, was very helpful and accommodating, and management throughout has been accommodating and very helpful. So none of this would have been accomplished, this combination of growth, fab, and transport, without the great facilities and people here at Purdue. So, I mean, to make this all work, we had to grow, we had to fab, and we have to measure low temperatures. And of course, Burke and the facilities and the group's work here has been crucial for this later establishment of Microsoft Quantum at Purdue. And so, there's these connections that I got lucky along the way, and had the great fortune to interact with all of these people. And I just even though these experiments happened over the last few years, it was a good 12 years in the making to get to this point, and a lot of people contributed. And I just want to thank them and Purdue for the opportunities it's given me. So thank you very much. Here's the team. I'll leave you with that. A year or two ago, I forget, but this is the group of students and postdocs, and I just want to acknowledge everyone's contributions. So thank you.
Thank you very, very much, Mike. There are a few questions. One question is, everything that you spoke about was in 2D gases. Could you just elaborate a bit on what the ramifications are if you go to 3D or 1D?
Yeah, sure. This idea of anyons is intimately tied to dimensionality. In the real world, 3D plus one time dimension, the fundamental particles are fermions and bosons. And the reason those statistics are what is available to us is pretty straightforward. If you do these permutations or braiding operations that I discussed in 3D, because of the topology, you can always deform them to an identity operator. These paths around a particle, you could always deform the path so the path taking goes not through the one localized particle, but underneath. And that's essentially, the operations can be related, are essentially an identity operator. So that's why we get fermions and bosons in 3D. In 2D, you can't do that. If you try to deform these braids, you actually have to cut through the particle you're trying to encircle. And basically, what are called these world lines form knots in 2D, where 3Ds you can essentially untangle the knots. And so, the dimensionality is crucial. nevertheless, these particles are real. They're the fundamental, as we can see in experiments, the fundamental objects of the 2D system we're talking about. Now, fractionalization can also happen in one-dimensional systems as well. It's a little bit more complicated to describe what a braid is. In 1D, you actually have to put networks together. But it can be constructed if you extend to networks. And so, but these are objects, at least as far as I know, that exist in 2D and in one-dimensional systems.
Okay, and I'd like to encourage the audience to submit any additional questions while Mike is here and available. There is another question. When does an electron gas go from 3D to 2D? What's the boundary? What determines that?
Okay. Well, that's dictated, let me see if I can zip back here, by this confinement. Let me see if I have a picture of the, here we are. So in the middle panel, there's two things plotted. The conduction band edge, which is essentially the potential that the electrons find themselves in. And as that potential, say that quantum well in the center around 160 nanometers from the surface, as that becomes narrower and narrower, you get quantization of the modes in the z direction. Okay, and basically when that length scale becomes comparable to the Fermi wavelength of the electrons you're considering, that's when the quantization basically happens. You can imagine if the box were really wide and the wavelength associated with electrons were short, the particle could bounce around as if it were in 3D. Now you start squeezing the box so its wavelength or length scale becomes comparable to the length scale of the electron wavelength, then the z motion can not take on any value. It can only take on quantized values that are separated by gaps. So what we mean by 2D is not strictly 2D that it has to be one atom thick, but really that at low temperatures that the electron system resides only in the ground state for the z motion and can't get to any other state that would allow effectively transport in the z direction. So it's basically where the quantum well, the box you put it in, becomes comparable to the wavelength of the electrons you're trying to confine. And you go to low temperatures and the system is not heavily disordered, other things. But it's particle in a box, basically, your elementary quantum mechanics problem.
Okay. What is the requirement for material purity? For example, electron mobility required to observe anyons?
Well, I can tell you what it was in these structures. For these types of devices, mobility is probably not the best metric, but the mobility was on the order of 7 or 8 million in the original one. It just has to be strong and pure enough that we can see a strong gap at the nu equals 1/3 state. Now, if we were looking at 5/2 or some other more exotic state, the constraints on or the reduction of disorder would have to be greater, but it's really, in this case, anything around 10 million will work just fine.
All right, Mike, thank you very much for a very interesting talk.
Thanks, Mike. I not only greatly appreciated you sharing the groundbreaking results this afternoon, but also acknowledging the many years of support and other scientists that you engaged with, and the importance of the really productive research environment and the capabilities and facilities that made all of this possible. So thank you for that. I'd also like to thank everyone in the audience for joining us for the Arden Bement Jr. Distinguished Lecture. The next lecture in the Distinguished Lecture series will take place on Friday, November 19th at 8:30 a.m. Yang Chen, the Carl Lark Horowitz Professor of Physics and Astronomy in the College of Science, Professor of Electrical and Computer Engineering in the College of Engineering, and the Director of the Purdue Quantum Science and Engineering Institute, will give the 2021 Herbie Newby McCoy Distinguished Lecture. I hope you all can join us for that as well. Thank you.